Hello, this is the Science Lesson 1.2 ebook reading that I am making. The title of this book is Using Scientific Tools, so I'm going to go ahead and open the ebook. It says to read pages 4 through 31, and that's quite a few pages, so we're going to go through all of them. Let me get to the right page, 4 through 31. Okay, and we're going to zoom in here if I can't. Nope, it didn't allow me to do that. Okay, so I'm going to go ahead and read it. Chapter 1, Using Tools in Science. We all use tools to get things done. To eat soup, we use a spoon. To move a heavy box, we use a cart. To sign our name, we use a pen. Every tool, large or small, exists to do a job. Tools extend us. Tools allow us to do things beyond our natural abilities. Some tools extend our physical strength, our reach, and our speed. Other tools expand the limits of our senses. Still others provide us with added brain power. In the purple box, it says, tools have been helping people throughout history. Spears and arrows aided ancient hunters. Early farmers made use of simple plows. For writing, people once used hollow reeds and wing feathers. And then in the little triangle over here, it says, the tools we use to measure things help increase our understanding of the world. The right tool. Without the right tool, many tasks are difficult or impossible, but a useful tool can inspire people to use it in various ways. One tool is not suited for all purposes, though, so inventors are always designing new and better tools for specific jobs. Scientific knowledge contributes to the invention of some tools. The light bulb, for instance, would not exist without knowledge of electricity. Likewise, earlier scientific discoveries made engines, televisions, and microwave ovens possible. In the purple box, it says, did you know the term technology applies to any practical use of scientific knowledge? Many nations are technologically advanced because the lifestyles of their citizens depend on technology. And then over here, it shows some of the inventions, past to present. So here's an old television and a newer style television. Here's an old boom box and how people use MP3s and audio players. Here's kind of an old light bulb, and here's the newer LED light bulb. And here's the old version of cell phones. They were satellite phones, and now we have new cell phones. All right, scientific tools are everywhere. Scientists, both young and old, use tools to help them find or discover information. From the simplest to the most advanced, tools are useful at every stage of the scientific process. Certain tools are ideal for observing and collecting information. Scientists rely on other tools to conduct experiments. To organize and store data and to share it with others, scientists make use of an even different set of tools. Wherever investigations into science take place, tools are in use. In laboratories, biologists use powerful instruments to study cells. Chemists use other devices to analyze substances. In the field, special tools allow geologists to explore the earth and astronomers to study the stars. Chapter 2, Tools that extend the senses. We use our senses to observe everything around us. For some scientists, though, that is not enough. They rely on tools that go far beyond what their own senses can take in. Observing far away. Telescopes make distant objects, such as planets and stars, seem bigger and closer. The optical telescope is the most common type. Just like our eyes, this telescope makes use of light. And in the little triangle box, it says here, in the early 1600s, Dutchman Hans Lippershey probably made the first optical telescope. Nearby in Italy, Galilei built and used a similar telescope to explore the sky. Types of telescopes. There are several types of optical telescopes. The most common is a refracting telescope. It has a long, tube-like shape. At one end is a large curved piece of glass called an objective lens. It collects light waves from distant objects. The lens works by slowing down the light waves passing through it. These waves take longer to go through its thick middle. As a result, all the different light waves reach the same point on the far side of the lens at the same time. This point is the focus, and a detailed image forms. A refracting telescope also has a small lens in the eyepiece. It allows the user to see the image even more clearly. The English scientist Isaac Newton was first to build a telescope with a mirror instead of a lens. The year was 1668. Today, most large telescopes are mirrors. This type of optical telescope is a reflecting telescope. The main mirror has a bowl shape. It reflects all the light waves that hit it. The mirror's shape forces the various waves to reach the same focus point at the same time. A smaller mirror reflects the waves again to an eyepiece or to an image-making device. Many large optical telescopes are housed in remote observatories. The Keiper Observatory, for instance, sits on a volcanic mountain in Hawaii. Each of its 2 optical telescopes uses a huge reflecting mirror. Sorry, not reflecting. Other types of telescopes pick up different waves from objects in space. Such waves include radio, ultraviolet, and infrared waves, even X-rays. Observing close up. A magnifying glass is a lens that makes objects look bigger than they really are, but it can only enlarge something 10 to 20 times. Microscopes, on the other hand, can make objects look hundreds or thousands of times larger. The optical or light microscope is the most common type. How an optical microscope works. The specimen on the glass slide rests on the stage. The mirror below reflects light up through the hole in the stage. The user adjusts the mirror to direct more or less light through the specimen. The nose piece holds lens systems or objectives. Each objective magnifies the specimen a different amount. The user rotates the nose piece to choose an objective. Microscopes with 2 or more objectives are compound microscopes. The eyepiece contains a lens that further enlarges the image formed by the objective lens. The user adjusts the focus by turning the coarse and fine knobs. Other optical microscopes. Some optical microscopes do not gather light all at once. Instead, they scan the specimen with a laser beam, spot by spot. A special device measures the light coming from each spot. A computer then uses this data to display an image on the monitor. Did you know one type of scanning microscope scans different depths of a specimen? The computer turns these differences into a 3-dimensional image. The user can view it from any angle. That's pretty cool. So the specimen is whatever they're looking at, okay? Waves shorter than light. To magnify a specimen even more, scientists often use an electron microscope. It forms images by using tiny electron beams rather than light waves. Some electron microscopes show detail less than 1 angstrom apart. An angstrom equals 1/10,000,000th millimeter, or 1/254 millionth of an inch. Wow, that's a lot. Today's high-powered optical microscope magnify a specimen up to 2,000 times. The earliest single-lens microscope made by Dutch scientist Anton van Leeuwenhoek magnified no more than 270 times. So we've come a long way in technology. Okay, page 22 and 23. Recording sights and sounds. Scientists who want to record what they see and hear use many devices. A camcorder is a commonly used tool for recording picture and sound together. This battery-powered machine has a built-in microphone. Some camcorders record onto magnetic tape. Newer models use memory cards. Many other types of recording devices are in use today. High-speed cameras, for instance, let researchers observe various processes in slow motion. Other cameras allowed scientists to shoot unnoticed at night. Still others operate deep in the ocean. Listening to animals. Special audio equipment is useful in picking up infrasonic sounds. These sounds are too low-pitched for human ears to hear. Low-pitched sound waves vibrate very slowly. Elephants often produce infrasonic sounds. And it says right here in the little pink triangle, medical doctors use machines that send ultrasound waves into the body. These sound waves are so high-pitched that humans can't hear them. An ultrasound machine converts the echoes of these fast vibrating waves into an image. Using this technique, a doctor can see a fetus inside a mother's womb. So it can see a baby inside before it's born. Wow. Chapter 3, measurement tools. An object's size and weight are both measurable. We can also measure such things as how far, how much, and how hot or cold. Even when and where are measurable. Although these measurements are different from one another, they all have something in common. Each one relates to a specific set of units that people have agreed upon. The metric system is a group of measurement units. All of its units, large and small, are built by using multiples of 10. This system is very useful to scientists because each unit is connected. For instance, the base unit of length is the meter. A kilometer equals 1,000 meters. Likewise, a kilogram equals 1,000 grams. Grams are the units used to measure weight. Did you know in the United States, people commonly use the customary units of measure rather than the metric? Inches, feet, yards, and miles are the units for measuring length. Ounces, pounds are used for measuring weight. Volume is in cups, pints, quarts, and gallons. There is no common system to connect these various units. Measuring temperature. A thermometer is an instrument for measuring temperatures of different gases, liquids, and solids. There are many types of thermometers. One common type is the thermal expansion thermometer. Thermal expansion thermometers have a long glass tube with a bulb at the base. Sealed inside the tube is liquid mercury. When the temperature goes up, the mercury expands and rises up the tube. When the temperature gets lower, the mercury contracts. The mercury sinks back down. The marks on the outsides of the tube are the temperature scale. This scale gives a value to the mercury's changing height. The value or mark relates to the scale used. Different temperature scales. Some thermometers use two different temperature scales, Celsius and Fahrenheit. Anders Celsius and Gabriel Fahrenheit were their creators. Both men lived in the 1700s. The most important points on these scales are the freezing point and the boiling point of water. The Celsius scale makes 0 the point at which water freezes. Water's boiling point is 100 degrees on this scale. The difference between the 2 points is 100 degrees. The Fahrenheit scale makes 32 degrees as water's freezing point and 212 as its boiling point. The difference between those 2 points is 180. Scientists around the world use the Celsius scale. Its 100-point system fits within the metric system. Did you know British physicist Lord Kelvin thought there was a limit to how cold something could get? In the 1800s, he created a temperature scale based on the idea that an absolute zero exists. Absolute zero, or zero, in the Kelvin scale is the same as negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. Measuring weight. Weighing devices have been around for a long time. The earliest type, called a balance, was popular in ancient Egypt 4,500 years ago. Even today, scientists use balances for weighing lightweight materials. Using an equal arm balance. This type of balance is used in making sure that two materials weigh the same. It has a horizontal bar that holds a hanging pan at each end. The user places one material with a known weight in the first pan. The other material goes in the second pan. If the first pan is heavier, it will drop. To reach an equal weight, the user adds more material to the second pan. Eventually, neither pan drops lower than the other. Usually a pointer shows that the pans are balanced. If so, the materials weigh the same amount. Triple beam balance. Another common weighing device is the triple beam balance. The mechanical scale weighs objects differently. However, it is still a balance because its job is to balance different weights. Spring scales also are a type of mechanical scale. They balance a load by using one or more springs. And there's a little experiment down here. They say you can try this. To weigh something, the user first slides the movable weights to the left side of the beams. The pointer should be at the 0 mark on the scale. Then the user places the object in the pan. The pointer will move away from 0. By moving the two heavier weight riders than the lighter one to the compact positions, the pointer will return to 0. Now the load is balanced. To read the object's weight in grams, the user adds up the 3 numbers marked by the riders. So that's what they're talking about here with the triple beam balance. They move it until it shows that it's zero, and then they add things to it, and then they can figure out how heavy it is. All right, and that's all we have to read out of this book today.